Ignoring crosswinds, there are 4 causes for this, but only 2 of them affect aircraft with nose-wheel landing gear. The first of these is produced by the torque reaction to the rotating propeller, which tries to roll the aircraft in the opposite direction, lifting the starboard wheel and forcing the port wheel down. Consequently, the rolling resistance of the port wheel is greater than that of the starboard wheel, and this imbalance creates a tendency for the aircraft to yaw to port until the wheels lift off. The second cause of swing during the takeoff run is produced by the propeller's spiraling slipstream and the resultant asymmetric airflow over the fin and rudder. This generates an aerodynamic force which tends to drive the fin to starboard and the nose to port. There are 2 more causes of swing during the takeoff run, but these only affect aircraft with a tail wheel. Obviously, the RPM of an upgoing blade is the same as that of a downgoing blade, and in level flight, the distance they travel in half a revolution, their relative airflows, and their angles of attack will be equal. But the beginning of the takeoff run will be in a tail-down attitude, when the axis of rotation is no longer the same as the horizontal path of the aircraft. This produces the asymmetric blade effect. Now the downgoing blade has to cover a greater distance than the upgoing blade in the same time, so its relative airflow is faster. Similarly, the angle of attack of the downgoing blade is greater than that of the upgoing blade. Therefore, the downgoing half of the propeller will be generating more thrust than the upgoing half, which will tend to yaw the aircraft to port until the tail wheel is raised and the propeller's axis of rotation is brought into line with the aircraft's horizontal path. The second cause of swing on takeoff, exclusive to aircraft with a tail wheel, is the gyroscopic effect. The force applied to the propeller as the tail wheel lifts off acts as though it is applied 90 degrees in the direction of rotation and produces a swing to port. Of course, in aircraft whose propellers rotate in the opposite direction, all these effects will be reversed, and those fitted with contra-rotating propellers will experience none at all. Today, propellers remain a very efficient means of aircraft propulsion, and their performance is superior to pure jets or turbojets at low subsonic speeds and medium altitudes. The advent of composites has enabled lighter, stronger blades with improved aerofoil sections to be manufactured. Nowadays, propellers are not only used to produce thrust, like these giant 21 feet diameter examples, but also to absorb energy to generate electrical power. Wind farm propeller diameters can be as much as 60 meters. What next? Who can tell? Could those who believed that jet propulsion would sound the propeller's death knell have envisaged an aircraft like this? With propellers producing lift for vertical takeoff, then turned through 90 degrees to provide thrust for conventional flight? Or like this, the prop fan, designed to satisfy the demand for greater fuel economy and reduced noise footprints. Propellers are older than powered flight, yet like the aircraft they propel, their development will continue to surprise, spurred by the application of new technologies. Strangely, since the birth of powered flight, one question remains unresolved. Should propellers push, pull, or do both? Clearly, the matter will be the subject for aerodynamic debate for years to come.